This is a solid sphere of radius r. Its surface area is 4 pi r square. This is a hemisphere. It has got two surfaces. One is curved and the other one is flat. The area of its curved surface is 2 pi r square. These two are known to almost all of us. This is neither a complete sphere nor it is a hemisphere. This is a chopped off portion of a sphere. What is the area of its curved surface? The formula for this is not that commonly known. In this lecture, I'll describe how to find the area of its curved surface. Before we proceed, we'll have to define the curved surface whose area we will calculate. This is the curved surface. It has, means this portion of the sphere has a flat round surface and a curved surface. The flat round surface is such that its radius subtends angle theta at the center of the whole sphere. Now question is how to find the area of this curved surface. As an analogy, we consider the area of the surface of an orange. How can we find this? A simple way is to peel its surface in the form of, as you can see in this figure, narrow round belts. Each such belt, when cut along its width and spread, becomes a rectangular surface. So let us see, this is one belt. When we cut it along its width, as I have shown it here, if you cut it along its width and then spread, then you will get this rectangle. Since the formula for the area of a rectangle is known to us, we can easily find the surface area of this particular belt. Now let us consider a particular belt. This is an element. It is in the form of a round belt, and we will define this belt as an element whose radius subtends an angle phi at the center of the sphere. So this particular belt, its radius is r sin phi. This is r. This radius subtends an angle of phi. So the radius is r sin phi, and d phi is an increment in the value of phi that corresponds to the width of the belt. We can calculate the width of the belt by using the formula A is equal to r into theta. A is equal to arc length, r is the radius, and theta is the angle subtended by the arc at the center of the sphere or center of the arc in this particular case. Here we find that this arc has subtended angle d phi at the center. Hence, the length of the arc, which acts as the width of this belt, is r into d phi. So r into d phi is the width and radius is r sin phi. We'll cut this belt along its width and we'll spread it, and then we get a rectangle whose length is equal to the circumference of this belt and whose thickness or the width is r into d phi. So this is the belt. Its length is 2 pi into r sin phi, which is actually the circumference of this 2 pi into radius r sin phi, and whose width is the width of this belt, which is r into d phi. Now you can see in this figure, in this photo, that there are multiple numbers of such belt. In fact, in order to get a perfect rectangle or as close as possible to a rectangle, we'll have to take the width of belt very small. Otherwise, if the width is not small, we will get a shape close to a trapezium. So this width has to be kept very small. Width is r into d phi, which is in fact very small, as d phi is a very small angle. So since the width is extremely small, we have got numerous such belts, rectangular belts, and the collective surface area of all these belts is equal to the area of the curved surface of the given portion. So we'll have to add all these areas, but manual addition is not possible here since there is a variable which is phi. Phi, the angle, is variable and its minimum value. We are measuring angle phi with respect to this line. So for a belt located here, the value of phi is close to 0. Again, for the extreme one, this is the extreme belt. For the extreme one, the value of phi is equal to, this is the angle phi, and its value is theta. So the limit of phi is from 0 to theta. So let us now consider the area of this elemental belt. Its area is dA. dA, which is the area of this element, equal to length 2 pi r sin phi multiplied by its width, which is r into d phi. So to get the total area, we will go for integration. A equal to integration 2 pi r square sin phi d phi. Limit for the variable phi, as we have discussed here, is from 0 to theta. Okay, this is equal to 2 pi r square cos phi. Integration sin phi is actually minus cos phi with limit from 0 to theta, equal to 2 pi r square into 1 cos theta, cos phi, cos 0 minus cos theta. Cos 0 minus cos theta means 1 minus cos theta. Okay, so this is the area of the curved surface of this portion. This is the curved surface. We have calculated its area. Area of this curved surface is A equal to 2 pi r square into 1 minus cos theta. So it depends on what? It depends on the radius of the intact sphere and the angle that the radius of its flat surface subtends at the center. We can now verify it very easily. If you put theta equal to, when you put theta equal to 90 degree, that means you are considering a hemisphere. When you are putting theta equal to 90 degree, you are considering a hemisphere, and if you put theta equal to 90 degree here, cos 90 is 0, and we'll get area equal to 2 pi r square. So area of the curved surface of a hemisphere is 2 pi r square, which is known to us and which we have verified here. Now again put theta equal to 180 degree. If you put theta equal to 180 degree, that means you are considering, we are measuring theta from this line, and we are measuring theta from this line, and 180 degree means you are considering the whole sphere. Then in that case, put theta equal to 180 here, cos 180 is minus 1, minus minus plus, and we'll get a equal to 4 pi r square. So we have not only derived the expression for the curved surface of a portion of a sphere, but we have also verified that this formula is correct. Okay.